Hi, welcome to part 1 of this module. Here we are focusing on whole number core concepts that should be emphasized whenever you are doing intensive intervention. So our objectives of this part are to talk about those core concepts of addition, subtraction, multiplication, and division. So let's think about whole numbers. Understanding whole numbers is really foundational to so many other things that students will do in mathematics. Students have to have a really strong understanding of addition, what addition means. And actually, as you'll see in just a few minutes, addition has 2 different meanings, and students have to know both of those meanings. Students also have to have a good, strong understanding of subtraction and how subtraction is related to addition. So how we can figure out a subtraction fact from an addition fact, for example. When we're thinking about whole numbers, we're also going to focus on the concepts around multiplication. And then finally today we'll talk about the concepts of division. And we'll really focus on different ways that students can interpret division, but also how division is related to multiplication and vice versa. Now these went too quickly there. These concepts that we're talking about today are related to the schemas that we discussed in the instructional strategies module. So some of these things might be like, oh yeah, I've seen that before. I've heard Sarah talk about that. I've been thinking about doing that within intensive intervention. So these concepts of the operations should be emphasized within problem solving, but really they should be emphasized whenever we are solving problems in the abstract. That's when we're solving any problem with numbers and symbols. So today we're going to kick off here with addition, and there are 2 concepts of addition that students should understand. The first concept is a part-whole concept, and when we talked about word problem schemas, we really talked about those as total problems. And the other concept that we'll focus on today is the concept of join. And when we were talking about the word problem schemas, that was really our change increase. So let's go ahead and talk about part-whole problems first. So here within a part-whole problem, we have parts, and we're putting those together for a total or for our whole. So when we're thinking about the steps to teach this, we're going to count one set with students, then we're going to count the other set, then we're going to move those sets and put those sets together to show the addition. And then we would count all of those for the sum. So I'm going to come back to this slide in just 1 minute, but I want you to focus on this problem 2 plus 3 equals 5, because I'm going to go over here and do this problem with manipulatives, and then I'll come back and show how that problem could be solved in the representational. So the first thing I'm going to get out here is I'm going to get out some type of tray or plate or mat or something that's going to be my workspace for the math. One of the things that students often do, especially when I start to get out a bunch of manipulatives, and if I'm moving them around counting, if I'm not like moving them onto a mat or moving off of the mat, many students can miscount. That's actually an error that students make very often with addition and subtraction. So I've got all my manipulative today. I'm going to use these frogs. I've got my frogs here, and then I'm going to bring them onto the mat as I'm using them in my problem. So remember, we were solving the problem 2 plus 3 equals 5. So the first thing I'm going to do is I'm going to get a set of 2 frogs. I'm going to put them over here. And to that, I'm going to add a set of 3 frogs. So I'll go ahead and put those frogs over there. So I've got a set of 2 and a set of 3. Now I want to show the addition. So I'm going to show the combining of these frogs. So I'll bring these 2 frogs onto the mat and these 3 frogs onto the mat. And now I'm going to count all of them together for the sum. 1, 2, 3, 4, 5. 2 plus 3 equals 5. Now if we want to think about that with the representational, we can look at a slide just like this one here. So here I've got 2 trains. So I've got 1, 2 trains. And to that, I'm adding 3 cars. 1, 2, 3. So 2 plus 3, and I can count all for the sum. 1, 2, 3, 4, 5. 2 plus 3 equals 5. Now this part-whole understanding of addition is really the initial way that students are introduced to addition. And they need to understand that I can add sets together because they go along with total word problem scenarios. And it's really how we think about adding initially, a set and another set, and we put those sets together for a sum. But we also have our join model of addition. And this is kind of a little bit further down the line in terms of students developing their mathematical understanding. So in the join model, we start with a set and we add onto that set, or something joins that set. So here we start with a set, and then we're going to add another set to it, and then we count to the sum. So let me show you what that looks like with our manipulatives. So here I've got my frogs again, and remember with the join model, I'm already starting with some frogs in the set. So I'm already going to start with my 2, all right? And now I'm going to count on these 3 additional frogs. So 2, 3, 4, 5. 2 plus 3 equals 5. And if I were to look at that in the representational, it would look a little bit like this. Here I've got 2. I've got my 2 trains. They're already there. And then these 3 cars are going to join the trains. So 2 plus 3, 4, 5. 2 plus 3 equals 5. Now, you might say, well, this is a little bit of a nuanced difference here. Why is it important that students see addition as putting parts together and then having an amount that it joins, or a change that is increasing? It's because we see these differences within problem-solving scenarios. And we also see these differences in the way that students use their fingers to count. So when the students initially solve this problem, they would say, okay, 2 plus 3. They would say 1, 2, and then 1, 2, 3, and then you've probably seen students do this, 1, 2, 3, 4, 5. So that's they've got a total understanding, or a part-whole understanding of addition. Now that's not totally efficient, and in fact for problems if I was adding 6 plus 7, I'm going to run out of fingers very quickly. So a more efficient counting strategy is to start with an amount and count on from that amount, and that's getting us to the join model of addition. So instead of saying 1, 2, 3, 4, 5, I would say start with 2. So 2, and then count on 3, 4, 5. So 2 plus 3 equals 5. And eventually, we would like students to understand the commutative property of addition, so the order of the addends doesn't matter. So I would actually start counting with the larger number. There it's 3, and then count on 3, 4, 5. 2 plus 3 equals 5. So let's look at your workbook activity number 1. You're going to look at this problem, 5 plus 6. And I want you to do 2 things. You're going to describe and draw, so you can't just do writing, but I want you to also do some drawing here, the 2 conceptual understandings of addition. So what would 5 plus 6 look like and be described in terms of a part-whole model? And what would 5 plus 6 look like and be drawn when we're thinking about the join model? So go ahead and do workbook activity number 1 right now. All right, keep your workbook activity number 1 out because you probably saw there's more problems within that activity, and we're going to come back to those in just a minute. But before you go to the next problem, we need to talk about meanings of subtraction, and you may want to emphasize these different concepts within intensive intervention. So within subtraction, we also have 2 conceptual understandings. We have subtraction as separating. So separating from a set, this will remind you a lot of those change-decrease problems. And then we also have subtraction as comparing. So comparing one set to another, that's going to bring back some memories of those difference problems that we worked on a little bit ago. So let's go ahead and think about subtraction with the separate model. Here I'm going to start with a set. And so you have this one set, and you're going to take away or separate items from that set. And then you will figure out the difference between once you've done that separation. So let me do this one with manipulatives over here. We're going to focus today on this problem, 5 minus 3 equals 2. I'm going to get my mat out again, so I kind of have a very designated workspace to do this problem. And the problem was 5 minus 3. So I'm going to start with 5 cubes. 1, 2, 3, 4, 5. And I need to separate or take away 3 of these cubes. So I'm going to separate them and I'm going to take them off the mat entirely. 1, 2, 3. So when I have 5 and I subtract 3, my difference or my answer is 2. Now, if I was doing that with these bears over here, this would be our representational model. I have my 5 bears, and the minus sign here, I'm going to signal that to separate or take away from the bears. So I'm going to separate 3 of those. 1, 2, 3. So 5 minus 3 equals 2. Now we also think about subtraction as comparison. Just with addition, where the part-part-whole model was kind of like the initial understanding of addition, and then the join model was a little bit more sophisticated, we're going to see the same thing here. The separate model is really kind of like the initial model of subtraction, and then the compare model is a little bit more sophisticated. So now we're going to think about this problem 5 minus 3 equals 2, but in a way of comparison. So I'm going to walk over here and get my manipulatives out. I'm going to remove my mat this time. I don't need it, but I'm going to compare 2 sets. The first set I'm going to compare is a set with 5 in it. 1, 2, 3, 4, 5. And I'm going to keep those all the same colored cubes just to show that that's a cohesive set. And then I need to subtract 3, all right? Now remember, this time I'm not using the takeaway model, I'm using the comparison model. So I got out 3 cubes, and I'm going to compare them here. So I have 5 green cubes and 3 red cubes. And this time, 5 minus 3, I want to figure out the difference or compare the difference between these sets. And it's this area right here. So what is the difference between these sets? It's 1, 2 cubes. So 5 minus 3 equals 2. Now if we're looking at this on our slides, I can do the same thing as the representation. So here are my 5 green cubes, and then I'm going to compare those this time to 3 blue cubes. So 5 minus 3, and the difference between these is this space right there. 5 minus 3 is 2, so that's the way that we can compare using subtraction problems. So back to that workbook activity number 1. Remember I said not to put it too far away. Now you're going to look at this problem, 8 minus 3. Same thing, I want you to describe and draw the 2 conceptuals of understandings of subtraction for this problem. So what would 8 minus 3 look like with a separate model? And then what would 8 minus 3 look like with a comparison model? Hi, I just look a little bit different, and that's because we are changing workbook activity number 2. We've done this math course with some teachers, and we received feedback, and they didn't exactly like the old workbook activity number 2, so here's a new one. Go to workbook activity number 2, and you're going to look at the work of 2 students, Martin and Lola. And I want you to read Martin's interpretation of addition and then figure out, well, what would be another way to explain addition to Martin? And then after that, you're going to look at Lola's explanation of subtraction and then figure out what would be another way to explain subtraction to Lola. So we talked about the concepts of addition as part-whole, and addition as join. We also talked about the concepts of subtraction as separate, and subtraction as compare. So guess what? There's multiple ways to think about multiplication. Haha, multiple ways to think about multiplication. That'll crack you up all day. So now we've got multiplication as equal groups and multiplication as comparison. Let's go ahead and look at what these different concepts look like. So with multiplication of equal groups, and that should bring back some really good memories from the problem-solving module. Equal groups was actually the name of the multiplication schema that we were talking about. Here we're going to show groups, then we're going to show the amount or number within each group, and then we'll count the product. So I'm going to focus on this problem 3 times 2 equals 6. So I'm going to move over here and get out my manipulatives. So the problem was 3 times 2. 3 tells me the number of groups. So I'm going to use these red plates, and I have 3 of them. 1, 2, 3. Now the multiplication sign said times, and I really like to interpret that as groups of. So I have 3 groups of 2. So that means I'm going to have 2 cubes in each group. So there's 1, 2 cubes in that group, 1, 2 cubes in this group, 1, 2 cubes in that group. So to figure out the product, I could count all of these. I could count 1, 2, 3, 4, 5, 6. Or when students are ready, they could count by twos. 2, 4, 6. So 3 times 2 equals 6. Now we can look at this problem representationally. Remember I talked about that multiplication sign as meaning groups of. So I've got 3 groups, there's my 3 groups, of 2, so 2 within each group. So there's 2 trains, 2 trains, and 2 trains. And what is our product? It's going to count, let's see, 1, 2, 3, 4, 5, 6. So 3 times 2 equals 6. Now I'm going to stay on the equal groups schema here, but I want to talk about another way that we can show this. So, and I'll just do this representationally here. We really want to set up students for success in mathematics across the grade levels. And one thing that students are encouraged to do in the middle school grades and into algebra is understand multiplication set up within an array. So here we can also use an array to show an equal groups model. So here I'm going to show 3 groups of 2. So there's one group of 2, another group of 2, and another group of 2. And so here I have 3 groups multiplied by 2, and that creates this array, this rectangular area here. And how many cubes are in this array? We have 1, 2, 3, 4, 5, 6. So 3 times 2 equals 6. This is still the equal groups concept. It's just visualized in a slightly different way. It's still 3 groups with 2 in each group. Now let's think about equal groups. We just thought about equal groups, so now let's think about comparison here. So we also can think about multiplication as a comparison, or how many times a set might move on a number line. I'm going to come over to my manipulative and show this one with a number line. I'll move my plates here. I don't need my equal groups any longer, but I do need this number line here. All right, so I'm still doing the same problem, 3 times 2. So here I've got my number line. This is a really nice number line because it does have an arrow pointing to numbers that are less than 0. It does include 0. And this number line actually goes all the way up to the number 30. So it gives students a good core understanding of whole number concepts along the number line. All right, so we're going to do the problem 3 times 2. That means I'm going to start at 0, and I'm going to make 3 jumps each time in increments of 2. So I'll start with 0, and I'll jump 2. That's 1, jump another 2, 2, and 3. So when I jumped 2 3 times, my answer is 6. So 2 times 3 equals 6. Now what would this look like representationally? Let me go ahead and show you that right now. So here I've got my number line. It's actually pretty close to the one that we just looked at. And I start with 0, and then I'm going to jump in increments of 2 3 times. So we've got 1 jump, another one, and another one. So 3 times 2 equals 6. Well, if we change one workbook activity, we have to change all of them. So now we are to workbook activity number 3. I want you to look here at problem A. And I want you to describe and draw the 2 conceptual understandings of multiplication. So think about how you would explain the equal groups meaning of multiplication, and then how you would explain the comparison meaning of multiplication. All right, now we're going to look at our last core concepts related to the operations. Here we're going to focus on the division concepts. We're going to focus on partitive division and measurement division. And let me go ahead and talk about what each of these means. With partitive division, we have a set of objects, or we have what we call our dividend. And we're going to divide those equally among the divisor, or among groups. And then we'll figure out how many are in each of those groups, and that will give us our quotient. So I'm going to use my manipulatives over here to solve this problem. And the problem we're doing is 6 divided by 3. So I'm going to go ahead and get out 6 of something. I'm going to use these 6 yellow cubes. 1, 2, 3, 4, 5, 6. And I'm going to share these 6 cubes among 3 groups. So I'll get out my 3 groups here. Now I'm going to do, this is usually what people will call an equal shares model. So I'm going to equally share these cubes among the groups. So 1 cube on each group. And I still have more cubes to share, so another cube on each group. So when I have 6 and I share them equally among 3 groups, my answer is 2. There are 2 on each group. Now, if I'm looking at that in the representational model, I'm going to look at my ducks here. They're yellow, just a little bit like my cubes. And with my ducks here, I have my 6 ducks, and I'm going to divide them equally among 3 groups. So there are my 3 groups. And remember, I'm going to distribute the ducks one at a time among the groups. So 1, 1, 1. There's still ducks that need to be distributed, so 2, 2, 2. So when I have 6 divided by 3, or 6 partitioned into 3 groups, each group has 2 ducks. Now we can also think about division in a measurement model. Here I'm going to show the dividend, so start with my 6, and then I'm going to make groups of the divisor. So how many groups can I make with the dividend, and then I'll count the groups. So let me go over here to my plates again. I'm going to collapse up the red plates there. So I'm going to start with my 6 cubes. And here I'm going to make groups of 3. 6 divided by 3. So I'm going to make groups of 3. How many groups of 3 can I make? Well, I can make 1 group of 3. I still have cubes to make into another group. I can make a second group of 3. So when I have 6 and I make groups of 3, I end up making 1, 2 groups. So 6 divided by 3 equals 2. And what would that look like representationally? Let's check out our ducks. Here I have the 6 ducks. And just that stuff fell on the floor. The ducks are okay, don't worry. So 6 groups made into groups of 3. So let's see how many groups of 3 you can make. 1 group of 3. And I've still got ducks left over, so I'm going to make another group of 3. So when I have 6 and I divide them and make groups of 3, 6 divided by 3 is 2. I'm back. Now it's time to do part B of workbook activity number 3. Here I'd like you to look at this problem and then describe and draw the 2 conceptual understandings of division. So think about the partitive meaning of division, and I'd also like you to think about the measurement meaning of division. Let's think about workbook activity number 4. In this activity, I want you to look at these word problems right here. There's 3 of them. And read through the word problems and think about what concepts of multiplication do you need to emphasize within intensive intervention so that students understand these word problems. And also think about what concepts of division you need to emphasize. Now, why have we been talking all about these core concepts related to addition, subtraction, multiplication, and division? We're filling your intensive intervention toolbox during this time. So you may not need all of this knowledge that we've been talking about but you might need some of this knowledge for some students some of the time. So we're just filling up that toolbox. But as you are thinking about doing this within intensive intervention, you really should keep these considerations in mind. First is that these concepts should not be taught simultaneously. They might be taught simultaneously within the same unit, but you shouldn't teach them, especially when you're introducing new material, on the same day. It would be very, very confusing to introduce total problems where I've got a part whole, and then addition problems where I'm also thinking about those in a join model. But if you are reviewing for students that have shown that they're having difficulty with different types of concepts, you can teach these together and actually have students compare and contrast to understand the differences in addition concepts, the differences in subtraction concepts, and also then how those are related. You know, join and separate are pretty closely related to each other. One means addition and one means subtraction. And remember these concepts of the operations, and we're going to see this a little bit later. We're going to work with multi-digit numbers. We're going to come back to a lot of these different concepts, and also all of these concepts would be really good to emphasize within anything you're doing with rational numbers. So addition of fractions or division of decimals or something like that. So let's look at our checklist here. So our question was, what whole number core concept should be emphasized within intensive intervention? So here are the things that we would like to see in intensive intervention. And remember, you might need to be doing these things with all of your students, but not always will you need to be doing all of these things with your students. So, but if you are, let's teach the part whole model and the join concepts of addition. We need to be teaching the separate and compare models of subtraction. We need to teach multiplication within an equal group scenario and a comparison scenario. And we need to teach division as partitive and measurement models.